Okay, so we are now moving to code verification, and that's basically the last topic of the semester. On Monday, I'm going to talk about the method of manufactured solution, which is one of the techniques that we use for code verification. And so Oberkamp and Roy detailed some simple tests that you can do to verify a code, like symmetry, conservation, Galilean invariance. Symmetry is sometimes tricky. That is, normally you would expect that if you apply symmetric loading and symmetric boundary condition, you'll get a symmetric solution. But it turns out that there are problems for which you can get non-symmetric solution. Buckling problems are typically, it's just that you can get both, let's say, a solution which is slanted to the left and one which is slanted to the right. Code-to-code comparisons, I've already told you. I told you this story about anti-optimization, where I got a very small differences between codes, and in order to convince people that there was an error, I had to magnify it. But this is a standard procedure, especially that we have codes that are essentially solve problems that are special cases of other problems. Like in solid mechanics, we may have a three-dimensional finite element model, but for beam type problems, we can also use a beam solution. So that would be an example. Could anybody give me an example from fluid mechanics? That is theories that are special cases of other theories. That is, so let's take the Navier-Stokes equations are considered to be the one that can solve any problem. What kind of simplification we make in order to solve an easier problem? I'm sorry? Incompressible fluid. So if we are testing Navier-Stokes code, we can generate conditions like low subsonic flow, where the flow is approximately incompressible, and check the Navier-Stokes code by using that solution. But, oh, I forgot to disable the timing. So this is sort of preliminaries, but most of these two lectures we are going to spend on discretization error, convergent test, and order of accuracy test, which are all related to discretization. And the reason that I've decided to emphasize this aspect is that this is the reality in codes that we typically want to verify. That is, we can use the codes that have already been verified for problems that are reasonably simple. Every decade or so, our computational capabilities improve, and we decide that we can do more complicated problems. So for example, when I started doing solid mechanics problems, companies like Ford and General Motors never considered to analyze crash. That was simply not possible with 1970s technology. Now they do it routinely. And so you basically are in a situation where you want to verify a code that you can barely afford to use. And so the discretization error hang over your head in that, yeah, you want to make sure that when you let the mesh become very fine, you'll get some analytical solution that you tested. It's just that you cannot afford to do that. So this is the problem that I'm going to focus on. So first of all, things that most of you have probably seen in a few other courses, but just to remind you, most of the differential equation treatments that we have rely on approximations that are based on Taylor series. And the thing that we do is that we take a Taylor series and we use only a finite number of terms. And the simplest approximation that we typically use is a linear approximation. So I wrote it on the slide. We have some function u of x, for simplification, just one-dimensional variable x. And u of x is u of x0 plus the derivatives times x minus x0. And that's the approximation, and the truncation will be proportional to x squared, or x minus x0 squared. We can be a bit more specific and say that instead of putting this order of, we can put the second derivative, 1/2 the second derivative at some intermediate point between x and x0, and that's actually the term that we are neglecting. So we have actually used that in the analysis of the paper helicopter that I showed you. That is, I solved for you the velocity analytically, but for the height or the distance traversed by the helicopter, I decided to use Euler integration. So I put that h of t plus delta t is h of t plus the derivative times delta t. Since v is the derivative of h, we just have here the linear approximation. And so since this is just the same Taylor series, instead of x we have t, the truncation error is O delta t squared. That is, if we take a time interval which is reduced by 50%, we can expect the truncation error to be reduced by a factor of 4. But that's not the discretization error. The discretization error is what we get after we apply this scheme to solve the differential equation. And in our case, the way I did it in class, I specified some final time, and we calculated the distance traversed. In the homework that you are doing, you basically have to turn it around. That is, you have a distance that is covered, and you need to use it to find the time. But what I'm saying is that even though the truncation error would be reduced by a factor of 4 if we reduce the delta t by 2, the discretization error will decrease only linearly, so that if we use half of delta t, we will actually reduce the error by a factor of 2 and rather than a factor of 4, and I'm asking why. Anybody can tell me why? No clue.
It's because Taylor series is a linear expansion, so you're only linearly decreasing error.
No, the error in that expansion is a quadratic that is changes quadratically. But think about what happens. As I said, the error in h of t it's basically the acceleration times delta t square over 2. Now, this is the error that we incur by going from h of t plus delta, from h of t to h of t plus delta t. That is, we incur this error if the acceleration was approximately constant. For example, if the helicopter was falling like a stone, then the acceleration would have been constant, and that makes it a bit easier to understand. And then we would incur an error that is just proportional to delta t over square, but we will incur it over half the interval. So if this is t, let's say that we need to go from t to t plus 1. And we divide it, before we went directly from t to t plus 1, or actually let's make it even more concrete. From 2 seconds to 3, and now we are going to take an intermediate result at 2.5. The error, let's say that this is the exact curve, the error that we incur here is half of what it was before, and the error that we incur here is half of what it was before, but they add up. So, I'm sorry, it's a quarter of what we had before. So basically, instead of having an error of 1, we have 1/4 plus 1/4. That is, the error at half of delta t is 1/4 of what it was for the full interval, but we accumulate it. So we are, each smaller interval gives us a smaller error. If you think about the error as money that you spent, then it's like if somebody charges you $1 to go to campus, and then they say, we'll charge you instead 25% to go halfway to campus. You are paying 1/4, but the cost of getting to campus is 1/2. So that's essentially what happens here. Each step has an error which is 1/4 of what it was before, but the step is only 1/2, so that to cover the whole distance, you need 50%. So this is just to show you that discretization error is not the same as truncation error. That is, the discretization error can change in a different way than the truncation error, and you can go and do an analysis for the differential equation that you solve and the discretization scheme and figure out what the order of accuracy is. That is, when you reduce your interval by a factor of 2, by what factor the discretization error will reduce. But a lot of time you just have to find it experimentally because the code is too complicated. So this is how we formally define order of accuracy. We have interval or mesh size h. I'm not exactly sure why everybody likes the letter h for mesh size. Anybody knows a word in English that begins with h that relates to interval size? I'm sure that there was some reason, but anyhow. So we basically say the error is proportional, the proportionality constant being g sub p, to h to the power of p, plus an extra terms of the order of p plus 1. So when h becomes very small, you can neglect the second term, and you will see that the error reduces like the mesh size to the power p. And so for simple problems like the helicopter or the Euler integration that we did, we can estimate it analytically. In our case, p was equal to 1. For more complex problems, we can estimate it by calculating a coarse mesh and a fine mesh. And now we have to distinguish between two cases. One case is where you know the solution, so that you know the error. That is, you analyze the problem with a fine mesh, you analyze it with a coarse mesh, you have an analytical solution like we have for the helicopter, and we can check the error. In such cases, we can say that we have two equations with two unknowns for p and g sub p, and the two meshes, a coarse mesh and a fine mesh, will allow us to estimate both GP and P. This is the case that we will deal with actually on Monday. Today, we are going to deal with the case where we don't know what the exact solution is, and so we need also to estimate what the exact solution is, so that we'll have one additional unknown, which means that we'll need 3 meshes instead of 2. Any questions so far? So this is called Richardson extrapolation. That is, you have some quantity that the code will solve for you. We'll call it f. And for a mesh size h, we'll denote it as f sub h. When h goes to 0, we will converge to f sub 0. And the error is like before, is gp times h to the p plus an order. And if we assume that our h is small enough to neglect the last term, then if we do it for 3 meshes, we'll get fh1, fh2, fh3, and we'll be able to solve for f0, gp, and p. As I said, you can neglect the last term when h is very small, and in a lot of problems where we need to verify codes, we cannot afford that. Furthermore, we are in a real bind, and the bind is that if we don't reduce the mesh in such a way that the coarse mesh also contains the fine mesh, we can be in trouble. And let me demonstrate that on the board. let's say that we have a nozzle that has this kind of geometry, and our coarsest mesh, let's say, has 4 elements in the x direction. And we decide that a finer mesh will have, instead of 4, it's going to have, let's say, 6. So, well, actually, let's say 7. And we will have the point is that with the original mesh, we capture the point where the geometry changes, and with the finer mesh, we don't. And that will introduce noise. Now, when you have a change, an abrupt change in geometry, you can look at it and make sure, for example, you can go to 6 and it will still capture the change in geometry. But the trouble is that oftentimes there is no abrupt change in the geometry, there is an abrupt change in the solution. That is, for example, you have a shock, or you have some other place where there is a high gradient, and by refining the mesh, instead of going near that, you skip it, and so that generates noise. So the people who can afford it and want to see how the effect of refinement holds with Richardson approximation, refine the grid by a factor of 2. And when you are in a one-dimensional problem, that's usually not an issue. In a two-dimensional problem, as we'll see from the examples, we refine the number of nodes by a factor of 4 every time we reduce by 2. In a three-dimensional problem, you are increasing it by a factor of 8, and a lot of times we cannot afford it. So this is part of the practical problem. So now just for fun, I put in something that we have 4 meshes with H ranging from 1 to 1/8, and the results are 20, 14.5, 12.5, and 11.7, and I'm asking you to guess what is the order, and when H will go to 0, what will you get? So let me that's not the one. Let's see. Okay. So again, the meshes are 1.5, quarter, and 1/8. And the answer are 20, 14.5, 12.5, and 11.7. Okay, I'm going to disable it in half a minute. Okay, so let me tell you, I don't know that there is a strictly the right answer here, but what I did is I took the error to be a combination of something times h and something times h squared, so that as h goes to 0, the order is 1. So by definition, the order is 1, and if I remember right, the answer is 11, so the third answer is the correct one. But if you look at the apparent order from those four, because of the fact that there is there is one term that is proportional to h to the 1 and one term that is proportional to h squared, you can say that in this range it changes like 1.5. So this was intended to illustrate the fact that the order of convergence depends on whether you can push it close enough to 0. Any questions about that? Okay. Okay, so there has been requests that I don't do only solid mechanics. So I dug into my history in verification and validation and found the fluid mechanics problem. So this is something that was part of the PhD of Serhat Hosder, who is now an assistant professor at, I think, Missouri, Technological University. And the purpose of this paper, the paper was presented 11 years ago, but it was published only 7 years ago. And the main reason was that getting results on the computers available then was horribly painful. So this is exactly a problem where everything slowed down because of the fact that when you want to push h to 0, you often do that you often simply cannot afford, and I wanted to show you the ambiguities that it creates. So I've taken some of those slides from Serhat's presentation, but not all of them. And this was his introduction, that we have Navier-Stokes solvers, and there is all kind of uncertainty, and it's worthwhile looking and seeing what happens when you try to analyze a problem for which you have experimental results. And to show that there is a problem, remember that the paper was presented in 2002, so Serhat took results from a year before where there was a challenge to generate drag polars. For those of you who are not familiar with the term, it means plotting the drag coefficient against the lift coefficient, which typically has a parabolic shape, but what you can see here are all the results that could be obtained for many different models. And so there is a problem in a lot of fluid mechanics simulation. And so the objective of that paper was to do a study of the magnitude of the uncertainty, and it was done for two-dimensional turbulent transonic flow in a converging diverging channel. And if you think about it, when you analyze what happens on airplanes, you typically need three-dimensional models. So in 2002, even doing two-dimensional models on transonic flow was a problem. So here is a depiction of the problem. That is, the colored part describes the flow field in the nozzle where you have a weak shock, that is the exit pressure, this is P sub E, over the intro pressure, which is on the left, is 0.82. That is, you are essentially generating the flow by putting a pressure differential between the entry and the other side. And if the pressure drops only by 18%, you will have a weak shock here. And you can see that in the abrupt change, it's not 100% clear because of the colors. On the other hand, if you reduce the ratio to 0.72, you have a strong shock. And furthermore, you have a pronounced separation bubble where the flow separates from the wall, and there is countercurrent in that separation bubble. So this is what substantially reduced the efficiency of the flow when you have a strong shock. And what you see here is the pressure distribution in red from the calculation, and the squares are from experiment. So in terms of the pressure distribution, can be viewed as a validation exercise rather than a verification exercise. And it looks as if we are capturing the pressure behavior fairly well, but that's not what we are really after. We want typically to capture the losses in the nozzle. That is, how much we lose because of the shock and because of the fact that the nozzle may not have the perfect shape to allow isentropic expansion. So there are the following kind of uncertainties. First of all, the one that we discussed before, the partial differential equations that we are solving can be Euler type, where we are neglecting the viscosity terms. We can have thin layer Navier-Stokes, and my knowledge of fluid mechanics is not enough to tell you what that exactly is. Full Navier-Stokes. There is uncertainty due to the fact that we don't really know the boundary conditions. If you think about it, if we can model the entire wind tunnel where this is done, we may be able to go far enough from where the nozzle is to know the boundary conditions, but we usually cannot afford to, so we start near and we don't have a perfect knowledge of the boundary conditions. We don't have perfect knowledge of the geometry. And the thing which is the present nasty one is turbulence model. Does anybody know why we need turbulence models? That is, supposedly the Navier-Stokes equation can capture everything in the flow. Why do we have turbulence model? Anybody remember?
Turbulence models because if you just solve it with light turbulence model, so what you'll be doing is you'll be solving a direct numerical simulation, and it takes a long time. It's computationally expensive.
Right.
So you model all the viscous terms.
So the answer is that it would be horribly computationally expensive, but the reason that it would be horribly computationally expensive is that you will need to capture the little eddies that develop there, and that would mean that your mesh will need to be extremely small. That's sometimes called direct Navier-Stokes. If you are going to a mesh size where you don't need a turbulence model, but you usually cannot afford to do that. And there is the discretization error and programming errors. And after going through this exercise, we don't really know if there are programming errors. That's an interesting question in itself. Codes like the one that we were using here, it's called GASP, are almost guaranteed to have programming errors, just because they are so complex, but they have been debugged, that is, they have been verified, which means that how can you verify a code and have a fairly high confidence in spite of programming errors? I can think of at least two reasons. Anybody? So the key is how big the error is and how frequently it happens. Okay, that is, you can have an error that will kick in only in some very unusual flows, but in other cases, like you'll have to take the square root of a negative number if the flow is really extreme, and whoever programmed it didn't consider that that can happen. So once in a blue moon, it happens, and either it crashes the code and you don't have any idea why, or it gives you bad answers and you are not aware of it. The other possibility is that there is an error in a term which is very small unless you invent an extreme problem for which the term becomes important, but nobody in the community is interested in that, so everybody can live with this very small error, and that's it. And you're almost guaranteed to have that. So this is the bottom two bullets, the upwind bias third order accurate row flux scheme. I don't have the faintest idea what it means, and if you do, that's fine. If you don't, it's really irrelevant to that. This simply is the discretization scheme, the flux limiter mean mod and van albeida. Again, I don't really know. Turbulence model, at least I know what turbulence model are, but the ones that were used were Spalart, Almaraz, and KW. And so I'm not trying to teach you or myself a bit of fluid mechanics because this is not relevant to the lecture today. What is relevant is what you see here. That is, we started with a 40 by 25 grid that has 1,000 nodes, and we ended up with 640 times 400 that has about 250,000 cells, so actually not nodes. And at that point, mesh number 5, a single solution takes 1170 hours if you used a single node. We were using 6 processors, so that reduces the calculation times to about 8 or 9 days. So this, I mean, I'm sure that we can do better today, but that was then. So we were interested in the nozzle efficiency that is done by enthalpy. And if you are not sure about what enthalpy is, it's not important. The important part is that if the nozzle didn't have a shock and it had the perfect profile, we will get isentropic expansion and we won't have losses. So we compare the losses to that. So this is something that we did to calculate nozzle efficiency with grid 1, 2, and 3. Remember that grid 2 is what we expect at that time, 10 years ago, practitioners to use. And we also went here for 0.72, that is the strong shock, to grid 4 and grid 5. Since, as I said, grid 5 takes 8 days, we couldn't really afford to go and do that here. And in terms of grid 2, for the weak shock, you can get reasonable results. Based on the other grids, we estimated that the error were 4% in the total efficiency. The discretization error was responsible for 3.5, and the turbulence model caused variability of 2%. For the strong shock, even with grid 4, you still had errors of the order of 10%. However, what is the most relevant to today's lecture is this slide, which basically says what kind of P we got. So first of all, unlike flows without shocks, there is no theoretical P. And this is because the P outside the shock is different from the P inside the shock, so that the overall you get some P that is somewhere between 1 and 2. And depending on the turbulence model, you got values that range between 1.3 and 1.6. And you can see estimating the error in the grid for those different models. We would range from 14% to 1% for the Spallard-Allmarat turbulence model, while for the strong shock and for the weak shock, we could go with 4 to 0.146%. So the message is that normally it's very expensive to do that, and these are the observations. So first of all, grid convergence is not achieved with the grid levels that most practitioners use. And you can say that was 11 years ago. Now it's different, and it's not. Could anybody tell me why not? Why the fact that computers are that much more powerful? Maybe we can cut down the calculation time by at least a factor of 10 compared to 11 years ago, maybe more. Why doesn't it still make the mesh converged? Yes?
The models are more complicated?
Yeah. I mean, this is, the more we can calculate, the more we push the complexity of our problems, and we always stop with the complexity at the point where the solutions are barely satisfactory. So this is just the fact of life. And so you are in such a state and you try to decide which model to use, like which turbulence model, then the discretization error interferes with your conclusions about the model. If the problem is nastier, like with shocks, you have to use much finer grids. And I guess that's all. So, any questions? Okay, that will be all for today.